This conference will now be recorded.
Hello everyone. Factors that affects nucleophilic substitution reaction. Some factors, that is 2 factors out of 4 we have discussed already. And in today's class, 2 more factors that influence nucleophilic substitution reaction that will be actually discussed. And if that part is complete, next we will start elimination reaction. And under elimination, there will be 2 types of mechanism. One is E1, another one is E2, and there will be some related problems. So here the problem that we have in the first slide, that is related to the solvent. That means the role of solvent, that idea we have to utilize here. So there are 4 solvents, A1, A2, A3 and A4, and the dielectric constant of those solvents. What is the order that is given? So you can understand here dielectric constant for A1 and A2, these two are actually same. And A1 and A2, these two solvents, they are dielectric constant greater than A4 and A3, where A4 is much greater than A3 and A3 is at the last point. And among them, that is among these 4 solvents, only 2 and 3, they can form hydrogen bond. So these 2 informations are given. First information given, dielectric constant order for these 4 solvents, and the second information is among these 4, 2 can form only hydrogen bond. Now the question that is asked, which of these solvents will be most suitable for SN1 reaction? So there are 4 solvents given, and we want to do SN1 reaction. We have to choose among these 4 which one will be capable for forming hydrogen bond. Now we know that when it is SN1 mechanism, then what kind of solvent we take? We take polar protic. But if it is SN2, it will be polar but aprotic. Now aprotic means no active hydrogen present. Active hydrogen means hydrogen when attached to any electronegative atom such as oxygen, nitrogen, we can call it aprotic. Protic. But if there is no such hydrogen directly attached to oxygen or nitrogen, that is electronegative element, then it will not be polar protic. Now SN1 reaction, here if we use protic solvent, what happens? The leaving group that is removed in the first step. The first step of SN1, we know this is the slow step. There is formation of carbocation and the leaving group is removed in the form of X minus. Now this X minus can be stabilized by hydrogen bond if there is polar protic solvent present. So just take very good example of water. Here water will face this X minus in such a way that only the hydrogen atoms, they will be facing this X minus because hydrogen bond formation is possible. So in this way the anion is stabilized. But suppose the same type of solvent, that is solvents where it is polar protic, same type of solvent if you use for SN2, now in this case also X minus, not only X minus but nucleophile, that will also be highly stabilized by all these that is the positive part of the solvent. But if the nucleophile is highly solvated, then obviously its nucleophilicity will be decreased, and we know that in SN2 the concentration of nucleophile, it matters, it is significant. But in case of SN1, concentration of nucleophile is not significant because in the rate expression you do not have any concentration term for nucleophile. So that is why polar protic solvent is best. Now here hydrogen bond formation is possible only for A2 and A3. So obviously you cannot take A1 and A4 because hydrogen bond formation, when it is there, it is better for SN1, not for SN2. So A2 and A3 only acceptable. But among these A2 and A3, which one is having more dielectric constant? So here we can see that A3 is having minimum value, but A2 is having maximum value. So considering all these factors, ultimately we can say which solvent will be most suitable for SN1. It is option B, that means solvent A2, not the other 3 solvents, A1, A3, A4. Okay, so is this clear? Should I repeat? Now the third point of factors that affects nucleophilic substitution reaction. Third point is nature of entering group or nucleophile. So you can call it entering group or nucleophile because it is actually the attacking part of the reagent. Fine. Now, so it is entering, not leaving. It is the opposite term of leaving group. It is entering group. So for SN1, the rate is independent of the nature of nucleophile. So remember the point that I have just mentioned, because here the rate expression is not containing any concentration term. So rate is equal to rate constant, then concentration of alkyl halide only, but there is no such concentration term for nucleophile. So that is why it is independent of the nature of nucleophile. So what kind of nucleophile you are taking, even if you are taking weak nucleophile, then also it's fine. But if it is SN2, here both the concentration as well as nature. So not just concentration, but nature means whether it is sterically hindered or not, all these factors you have to take care of. Here the rate expression is K into concentration of Rx as well as concentration of nucleophile, both. So that is why in case of SN2 it is important, right? Now when we are talking about that concentration and nature of the nucleophile, we have to keep in mind concentration is fine, but what is by nature, what we are trying to say, nature is the nucleophile should be small in size, it should not be very sterically hindered. Then attack towards the R part by the nucleophile, that process will be difficult. Then the nucleophile, it should be less electronegative, because the nucleophile, when it is carrying some charge, and if it is very electronegative, so what will happen, it will tightly attract this negative charge. But if it is so, then there will be less tendency for donation. Fine. So just take two examples. Suppose you have Rx and the nucleophile you have taken. In one case you have taken alkoxide, that is RO minus. Another nucleophile you have taken is not oxygen. Now it is suppose sulfur. Now oxygen is more electronegative, right? So the negative charge that is present over oxygen, this kind of donation towards the R group, and also if you consider RS, obviously for RS it will be easier process for donation of this electron. So this negative charge can be easily donated because it is less electronegative. So that is mentioned in the second point, that nucleophile should be less electronegative. That atom which is actually carrying the negative charge. We are not talking about the other part of the nucleophile. Just focus on that atom which is actually carrying the negative charge. It should not be very electronegative. So if these two we compare, obviously RS minus is better nucleophile compared to RO minus. And the last point, nucleophile should be strong base. Now basicity and nucleophilicity, there is some correlation. So when there is correlation, that is both nucleophilicity and basicity, mostly they are correlated. That is, when it is good base, it is good nucleophile. When it is good nucleophile, it is good base. But in some cases it may not be so, but mostly as it is so, so that is why you can say that it should be strong base. Now here we will see the definition of a nucleophile and also the definition of base, so that you can understand the difference between these two. A nucleophile is a molecule that attacks carbon atom in substitution reaction. So nucleophile, we know it is electron rich species, so it will try to attack some electron deficient carbon. So this carbon which is present in alkyl halide, the R part, it is electron deficient because of this presence of X. But when it is base, base is also electron rich, just like nucleophile. But try to understand the difference. When it is base, it is actually, what will do, it will deprotonate the substrate in an elimination reaction. So the term nucleophile we use in case of substitution reaction, and the base we mainly use in case of elimination reaction. So nucleophile, it always attacks electron deficient carbon, and base always attacks H. That means it always takes H plus, so that is, it is deprotonation. So that is the difference between nucleophile and base. Fine. So the same molecule can act as nucleophile or base in different situations. So same molecule depending on the other condition of the reaction. Suppose you are controlling the temperature or concentration. So depending on so many other conditions, same species can behave as nucleophile or base. So that is why you will see When you have kept the alkyl halide part same and you are just changing the condition, but the species that you have taken as reagent, it can behave as nucleophile in some cases, but if you are changing the condition, then it can also behave as base. So when it is behaving as nucleophile, it will attack some carbon, and when it is base, it will attack H. Fine. So this is the difference. So we can say that as if base is a kind of nucleophile, but nucleophile is broader term, base is narrower term. Here we have some examples of nucleophiles so that you can have proper idea about different kinds of nucleophiles, and also what is their order for nucleophilicity, because order of nucleophilicity, suppose some species are given, all can behave as nucleophile, and it will be asked in the question that predict their order. So we have to understand which is better nucleophile, which is not. Okay. Here, the first nucleophile, these three members, as you can see, Cl minus, Br minus, In. So all are basically halogen. Now among these three, chlorine is maximum electronegative, that is electronegativity if you consider first chlorine, then bromine, and then iodine. So as we know that it should be less electronegative, right? So that means I as it is least electronegative, it will be behaving as beta nucleophile. So beta nucleophile will be I minus, then Br minus, then Cl minus. Next we have two pairs, water and HO minus. Now see, among these two, as if when you have removed one H, then you are getting HO minus. Now here we have lone pair, which will be attacking as electron density, which will attack some electron deficient center. But here you have fully developed negative charge. Fine. So that is why among these two, HO minus will be better nucleophile compared to H2. Then we have ROH and RO minus. This is also same. Here you have OH. So this lone pair will attack. But here you have negative charge. So that is why this will be beta nucleophile. And then we have RCO2 minus. Fine. Here also we have negative charge over oxygen, and here resonance is possible. This type of resonance is possible. You can get another resonance structure. So this is also another type of nucleophile that can be used. If this R group is CH3, it will be called acetate R. That is CH3COO minus. Fine. Next, H2S and HS minus. These two also same problem. So HS minus, as it is having more negative charge, it will be behaving as beta nucleophile compared to H2S. And if you compare among these two, now the explanation is different. Now among HO and HS minus, obviously HS minus is beta nucleophile, because now the negative charge is over less electronegative atom, but here it is over oxygen, which is more electronegative. Okay, so you can compare HO and HS based on this second point. Okay, and next we have RSH, RS. This is also same explanation. Then ammonia, it can also act as nucleophile. N3 minus, that is 3 nitrogen carrying single negative charge, and water. Then Cl minus, ammonia. This is actually ammonia. Then cyano. This is negative charge over sp hybridized carbon. So how you can get these nucleophiles? Suppose you have RC triple bond CH. If you remove this H, there will be negative charge over carbon. This negative charge is stable because this carbon has some electronegative nature. As it is sp hybridized, S character is very high. And NC, this is another kind of nucleophile. So as it is ambient nucleophile, negative charge, it may be over carbon or it may be over, sorry, it is actually same species written two times. Okay, you can consider only one. NC. So this is generated from molecule like KCN or NaCN. So K plus, Cn minus. So negative charge is present over carbon. So this is cyano, which is also it can also act as nucleophile. Fine. So this slide, it is all about nucleophilicity, and that is the order of nucleophilicity. And also here we have some idea about the difference between the nucleophile and base. So these two terms, they are actually very similar terms, but still there is some difference. Next we'll see, the point is we are still discussing this factor, which is nature of nucleophile or entering group. Now, parallelism between nucleophilicity and basicity. So parallelism means when the nucleophilicity and basicity both are same. Suppose you have two species, X and Y, which can behave as nucleophile or base. So when we are saying that parallelism is existing, that means if X is more nucleophilic than Y, then X is also more basic than Y. That means same type of order, both for nucleophilicity and basicity. So when it will exist, we can say that there is parallelism. But if it is opposite, suppose as nucleophile X is better than Y, but as base Y is better than X. So in this case, parallelism is not existing. That is the difference. So first we will see when it exists, because most of the time you will see that it is existing. Now under this exists, when we are saying that parallelism is existing, then two different possibility we will see. Same attacking atoms. So this nucleophile, as you can see, methoxy, then HO minus, PHO minus, all are having same atom, that is oxygen atom, which is basically the attacking atom. Now when it is same attacking atom, under this condition, this is a very good example. So the order that you are seeing here, first methoxy, its nucleophilicity is maximum, then HO minus, then phenoxide, and then acetate. This is acetate ion basically. This is formate ion. So this is the order of nucleophilicity, and this is also the order of basicity. Fine. Now here, how you will understand that it is that is why it is the basicity order. So see, if you consider the corresponding conjugate acid, that is methanol, here it is water, then phenol, then acetic acid, that is MeCOOH. So all these are corresponding acid. Now when you have any acid HA, suppose in general you have any acid HA, it is dissociating as H plus and A minus. Now this A minus is basically all these ions, MeO minus, HO minus, PHO minus. And remember, this A minus, it is also basically the conjugate base. Now conjugate base, if it is very stable, what will happen? The dissociation of HA to H plus and H minus, A minus, that is also high. That means when conjugate base stability is very high, then acidity of HA, that is also high. These two are directly related. Okay. So as this A minus is very stable, so HA will be more, it will be dissociated to H plus and A minus in more amount. That means ionization high, concentration of H plus high, so acidity high. So when conjugate base is very stable, acidity is also very high. Now we know that when it is acetic acid and methanol, obviously acetic acid is more acidic, right? Now as it is more acidic, so the corresponding conjugate base, which is acetate ion, that is very stable, but methanol is not so acidic. So the corresponding conjugate base, it will be it will not be very stable. So here acidity of, that is CH3COOH, it is greater than MEOH. That means the corresponding conjugate base, when you will consider, that will be, that is, this is not very stable. So as its acidity is less, so corresponding conjugate base, that is actually unstable. And as it is unstable, so that is why it's very reactive. So that is why it is at the left hand side, that is maximum nucleophilicity is possible for MEO minus. It is not very stable, it is always searching for some H or some electron deficient carbon, so that it can stabilize itself. So This is, in this way you can understand why the order is like this. That is, the basicity order is like this. Similarly, when it is same, attacking atoms are from same period. So see here we have negative charge over carbon, which is methyl anion, then nitrogen, then oxygen, and then fluorine. So all are from second period. So as all of them are from second period, carbon is from 14, nitrogen from 15, oxygen from 16, fluorine from 17. So they are from same period. All are basically same. Now when they are from same period, you can see as we are moving towards higher group number, that means electronegativity is increasing. So when electronegativity is increasing, that means this negative charge is very stable over fluorine, but here negative charge you have over carbon, which is not very stable. So as the negative charge is not very stable, so that is why it is very reactive, and as it is very reactive, so that is its nucleophilicity is also high. Okay, so that is why in the first position there is methyl, then as gradually the electronegativity of the atoms, which are basically carrying the negative charge, as the electronegativity is increasing, it is becoming more and more stable, and its reactivity is decreasing. So that is why this is the nucleophilicity order. You can also say this is the basicity order. And if you want to give the explanation in terms of acid, that also you can do. So when it is methyl, the corresponding acid is methane. When it is NH2 minus, corresponding acid is ammonia. When it is HO minus, it is H2O. When it is F, it is HF. Now acidity for these four molecules. This is the order. This is maximum acidic. So as it is maximum acidic, the corresponding conjugate base, that is F minus, that is very, very stable. So as it is very, very stable, its reactivity is minimum. And in this case, that is methane, the corresponding conjugate base, it is not stable at all. That means its reactivity is very high. So that is why this is the order. So in this, that is the discussion that we have done, when there is parallelism existing between nucleophilicity and basicity, is there any doubt? Because this, that is the last 5 or 10 minutes, whatever we have discussed, that is very important, not just for this chapter, haloalkane and haloalkane. If you have proper clear idea about the conjugate base, its stability, its reactivity, and the corresponding acid, if you have this idea clear, you can answer different types of questions, not just for this chapter, which is basically organic, but you can also answer for inorganic chemistry, the basicity order, or conjugate base stability order. All this you can easily answer. So that is why I am asking, is there any doubt? Should I repeat this part once more? Next we will see when parallelism is not existing, then what will happen. So when it is not existing, do not exist, but remember it is only for polar protic solvent. If you have taken polar aprotic solvent, then it will exist. Okay. So remember, it do not exist. Just consider that it is. We are doing this discussion for polar protic solvent. Now, what happens when attacking atoms are from same group? So here we have nucleophilicity for I minus, Br minus, Cl minus, F minus. So different group, same group. So all these halogen, they are from group 17. So as you are moving down, fluorine is from second period, then third period chlorine, then fourth period, and then fifth period. So as you are moving down, nucleophilicity is basically increasing. But if you are considering basicity, now the order is reverse. Now the order is different. F minus maximum basic, then Cl minus, then Br minus, and then I minus. Now this is true only for polar protic. So when we have taken polar protic solvent, then what happens? Then hydrogen bond formation is possible. But if it is polar aprotic solvent, then hydrogen bond formation is not possible. And in that case, both nucleophilicity and basicity, they will be correlated. That is, there is parallelism existing. But when it is polar protic, then hydrogen bond formation is can form very easily between F minus and suppose there is water molecule as solvent. But this type of hydrogen bond formation is not possible as the size of the ion is increasing. So we know that hydrogen bond formation, there is some criteria. The criteria is the atom must be very electronegative and it should be very small. So basically, hydrogen bond formation is possible only with 3 elements in the whole periodic table: fluorine, oxygen, and nitrogen, because these 3 elements are the most electronegative elements, right? Sometimes there is also possible with chlorine, but it is very weak. Mainly, hydrogen bond formation is possible with fluorine, oxygen, and nitrogen, these 3. So that is why here with I minus hydrogen bond like this is not possible. So as here hydrogen bond formation is not possible, so the I minus ion, it is relatively in free condition. Now if the nucleophile is free condition, obviously its nucleophilicity capacity, it will be very high. So it can easily attack. Suppose there is any alkyl halide and you are using some polar protic solvent, then I minus can easily attack R because it is relatively free. But F minus, it is interacting with water molecule, it is not relatively free. So that is why I minus will be better nucleophile compared to the others. And this is the order. As the size is increasing, nucleophilicity is also increasing. But when it is polar aprotic solvent, this type of hydrogen bond formation, that question does not arise. So now both F minus and I minus, both will behave almost in a similar order. Now also nucleophilicity, it is high for I minus because here electronegativity of I is less than F, so it can easily donate electron density. And also when you are considering basicity, then also the same order. Fine. So should I repeat any part in this slide? And the last point, which is nature of leaving group. Now leaving group means as we are discussing this under haloalkane and haloarene chapter, so leaving group we mainly consider Rx, that is halogen. It may be I minus, Cl minus, Br minus, I minus. But basically this nucleophilic substitution reaction, it is not just for haloalkane or haloarene. This is a very versatile topic. So other types of leaving groups are also possible. Here for both SN1 and SN2, the effect of leaving group is same. So you don't have to understand it separately for SN1 and then for SN2. Actually it is same. Fine. So in SN1, the slow step is involving cleavage of this bond. So if a leaving group is very good, the bond can be cleaved very easily. And in SN2 also, as it is single step reaction, only one step is there. So if you consider the transition state, the bond is just starting to break. That is the bond between R and X. I am using dotted line because it is as if it has just started to break. And also other side, the bond between nucleophile and R it has just started to form. So that is why if X can be removed very easily, then this negative, this is actually the transition state for SN2, and the Lg starts acquiring a negative charge. So there is partial negative charge, not fully, also partial negative charge over nucleophile. So it just start acquiring a negative charge as Ts is reached. Ts means transition state. So as we go from left to right on the periodic table, the ability to be a good leaving group, that is actually increasing. And we know that halogens, they are at the right hand side extreme because they are from group 17. So if you consider halogens, they are actually very good leaving group, both for SN2 as well as SN1. So as from this line you can understand, halides will be very good example of leaving group. And remember, weaker bases acts as stronger leaving group. Now weaker base means what? Stable base. Weaker means where reactivity is very less. Reactivity less means it is very stable. It has no tendency to take part in reaction. So weaker base, that must be very good leaving group. That is strong leaving group. Stronger or good leaving, whatever you say. So here the order for nucleophilic, leaving group capacity is I minus maximum, then Br minus, Cl minus, and F minus. And see here I minus is basically weaker base. So weaker base means it is very stable. It can remain independently as I minus. So that is very stable. But F minus, as it is very strong base, so it will always search for some H. So it is not stable. So as it is not stable, it is not very good nucleophile. Now we will see some more examples of leaving group, because I have already mentioned that leaving groups, they are not limited to only halogens. There may be different types of nucleophiles also. So that is why, though it is not related to haloalkane or haloarene, but still when we are discussing nucleophilic substitution reaction, that is SN1 and SN2, you should have proper idea about all the other types of leaving group that are possible. And see here what kind of leaving group we have. CH3, then SO3 minus. Here it is known as methyl sulfonate, and it is very, very stable because resonance stabilization is there. What kind of resonance? See the negative charge, it can take part in resonance with the double bonds. Now you are getting another equivalent resonance structure like this. It is equivalent, isn't it? Then similarly, this there can be again bond formation between O and S and negative charge over the other oxygen. So these three resonance structure that you are getting all are equivalent, so they are resonance stabilized. So as it is very, very stable, so that is why they are very good leaving group. So these two are examples of very good leaving group. And the second one, which is known as tosylate ion, here also same kind of resonance is possible. Fine. And if you consider the corresponding acid means CH3, SO3H, and for the other one it is CH3, benzene ring, SO3H. So this molecule is also known as tosic acid. In short, it is written as TSOH. So TSOH is very highly acidic. So that is why its conjugate base, which is this tosylate ion, that is very stable. And this is methane sulfonic acid, CH3SO3H. This is also very strong acid. So obviously the corresponding conjugate base will be very stable base. So as it is resonance stabilized base, both are basically. So they are very good leaving group. So these two are examples of very good leaving group. Okay. So as we are saying, writing the corresponding acid as TSOH. So this conjugate base you can write as TSO minus, tosylate ion in short, TSO minus. Here we have two examples where the starting material is different. See, in the first starting material, NH3 plus, that is the bond between carbon and NH3 will be cleaved. Reagent is same, NaOH. So HO minus is the nucleophile here. In the second case, carbon and bromine bond will be broken. Now in the first case, the leaving group is basically ammonia. In the second case, the leaving group is bromide. Now if I ask that among these two reactions, in which case the reaction will be, that is reaction rate will be high. So it is obviously for the first one. First one will give better result than two. Why? Because in the first case, the leaving group that you are seeing, it is neutral. And here it is anionic. Though we know that halides are good leaving group, but still, see, the logic is here, any negatively charged species, it is compared to any neutral molecule, obviously it is less stable. So here NH3, as this is neutral molecule, it will be more stable compared to Br minus. So as the leaving group is more stable, so this bond can be easily, we can break, and that is the reason in case of the first reaction, reaction rate will be high. Is this clear? One more example. Here starting material is not alkyl halide. Here we have taken RCH2H. But here we'll try to see that whether the reaction will move towards left to right or the reverse reaction will be feasible. So for that, see, Here nucleophile we have taken cyano minus. So it is attacking this carbon, carbon-oxygen bond broken. This is the leaving group. Now, if you consider the opposite reaction, suppose you are considering the opposite reaction. Now, RCN is the starting material and HO minus is behaving as nucleophile. It is attacking here and CN is removed. Now, the question is, which side will be predominating? It will move from left to right or right to left. That is, in which side equilibrium will be more shifted. Now, to answer this question, you have to understand that among these two leaving group, in one case, HO minus is the leaving group when you are moving from left to right, and when you are moving from right to left, now cyano is the leaving group. Now, among cyano and HO minus, cyano is better leaving group. So, cyano is better leaving group compared to HO minus. So, that is because, why it is so? Because it is more stable. So, as it is more stable, so its leaving group capacity is high, and as leaving group its capacity is high, so here the reverse reaction, that is right to left reaction, that reaction will be feasible. That is, from cyano you will get RCH2H, but the reverse reaction is not feasible because CN minus is better leaving group compared to HO minus. So in this slide you can see not just halide ions, but there are different kinds of nucleophiles possible. So here I am trying to give you some broader idea about the nucleophiles so that any type of question related to nucleophilic substitution reaction you can answer, which is not just limited to alkyl halide, because when it is alkyl halide, leaving groups are halides, but there may be different types of starting, that is the substrate for nucleophilic substitution reaction. So here you can see the substrate we are using RCH2H or RCH2CN. So this is a kind of substrate that we can use in nucleophilic substitution reaction. Then it may be CH3SO3. So suppose instead of RX, you have RSO3, RSO3CH3. So this is also an example of substrate that you can use in nucleophilic substitution reaction. Fine. So nature of leaving group, all these points that we have discussed. Is there any doubt? So after finishing substitution, next we have to see elimination reaction. Okay, because remember the four main types of reaction are there for chemical behavior of haloalkanes and haloarenes. Among these four types, the first one is completed, which is nucleophilic substitution. Now we have reached the second type of reaction, which is also very versatile. Mostly these two reaction types, that is substitution and elimination, these two are mostly important for haloalkanes and haloarenes. And after finishing these, two more reaction types will be there, but they are not so versatile. So see what is elimination reaction. As you can understand from the term elimination, that means some part will be eliminated from the molecule. When it is substitution reaction, you have seen it is substitution of one part of the molecule by the other part, but there is no such elimination. Here halide is going, some nucleophile is coming. Fine. Substitution, replacement. But now elimination means some part of the a small part of the molecule that will be removed completely, or better I say eliminated completely. That is why the reaction is elimination reaction. So when we have taken haloalkane, which is containing a hydrogen on beta carbon, is treated with ethanolic solution of KOH. Now here this term is important, ethanolic solution, because if you have used aqueous solution of KH, there may be a chance of substitution reaction, because in aqueous solution KOH will remain in highly ionized state, that is HO minus. Okay, so there will be a chance that it will act as nucleophile, but here we want the reagent to act as base, because it is hydrogen removal, it is deprotonation, so it must behave as base now, not nucleophile. So if you are using this type of reagent, there will be formation of CC double bond, that is alkene. Now here, as we are saying that hydrogen on beta carbon, so this hydrogen which is present on beta carbon, you can call it beta hydrogen. So sometimes these elimination reaction, they are also known as beta hydrogen elimination. So look at this. We have taken this alkyl halide. There may be any other groups, that is not important. Just focus on this fragment, which is CH single bond CX, and you are using alcoholic KOH. Now what will happen? This H, which is basically beta hydrogen. Why it is beta hydrogen? Because with respect to halogen, this carbon is alpha carbon, this carbon is beta carbon. So the beta carbon, if it is containing any hydrogen, that will be, we will call it as beta hydrogen. So beta hydrogen is removed. So this CH bond will be broken and CC double bond will be formed, and CX bond, that will also be broken. So as if here HO minus is capturing this H, and X minus that is removed, that is now attached with K. So that is why here it is written the byproducts are KX and H2. So this is a general expression. Now come to actual example. Suppose you have taken bromoethane. Now this is alpha carbon, this is beta carbon. So you have total 3 beta hydrogen. Any of this hydrogen can be removed along with this Br. Ultimately you are getting CC double bond. So there are 2 carbons. It is known as ethene or ethylene. Then if you have taken 2 bromopropane, or you can also call it isopropyl bromide, then this is alpha carbon, this is beta, we have another beta. But these 2 beta carbons are equivalent because it is symmetrical structure. So any of this hydrogen, there are total 6 beta hydrogen, 3 here, 3 here, total 6. So any of these 6 beta hydrogen can be removed, and in all cases you will get the same molecule, which is propene. It is 3 carbon, but there is double bond, so that is why it is propene, not propane. In this reaction, a double bond is formed between alpha carbon and beta carbon by releasing a halogen attached to alpha carbon and a hydrogen which is attached to beta carbon of the starting material, which is haloalkane. Now as beta hydrogen is removed, so it is also called sometimes beta elimination reaction or dehydrohalogenation. Why dehydrohalogenation? Because it is net removal of, see, let me clear it. Dehydrohalogenation means what? Removal of H and X. So together it is hydro for H, halogen for X, and D means it is removed. So it is net removal of H and X, right? And there is formation of double bond here. So that is, it is also called dehydrohalogenation. Remember, when it is removal of water, we call it dehydration. And when it is removal of HX, we call it dehydrobromination. So this D term is always used whenever there is some elimination. Probably you also know that when carbon dioxide is removed, we call it decarboxylation, right? So D, whenever we are using, that means there must be some removal. Now for this elimination, here are the examples that you have seen. For the first one, there is actually formation of these 3 beta hydrogens, all are equivalent. In the second example also, all these 6 hydrogens are equivalent. So there is no chance for formation of 2 different types of alkene. It is always one type of alkene. But suppose when more than 1 beta hydrogen atoms are present, not just more than 1, I mean to say more than 1 different type of beta hydrogen. Because here also you have total 6 beta hydrogen, right? So just if you are saying more than 1, it is not enough. When more than 1 different types of beta hydrogens are present, then there is a chance of 2 types of alkene product formation. And then you have to consider this rule. And what is the rule? The preferred product, that is which alkene will be measured, how we will understand. So to understand that, to predict the measured product, you can take the help of Sedgwick rule. And it is saying that the preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atom. So you have 2 doubly bonded carbon atoms, and there will be total 4 positions where there may be some alkyl group. Okay, you have to count the alkyl group, and here is the number of alkyl group, here will be the chance of formation of that alkene according to Sedgwick rule. But sometimes Sedgwick rule may not be followed, and there is another rule for that, which is known as Hoffman rule. Now mostly it is Sedgwick rule that is followed, Only there are some special cases. Then you will see that Hoffman is predominating. But first we'll see the example where ZJEP is predominating. Here we have taken the starting material 2-bromo, 2-methyl butane. So 2-bromo, 2-methyl means this is 1 carbon, this is 2, this is 3, this is 4. So at 2 position we have substituent Br as well as methyl. So that is why the name is 2-bromo, 2-methyl butane. Now as bromine is attached to these 2 carbon, this is alpha carbon, but both sides there is beta. And now both beta carbon, if you look carefully, their chemical environment is not same. So here you have 3 beta hydrogen, here you have 2 beta hydrogen, but their nature are not same. Now see, 2 different types of product formation possible. If hydrogen is removed from 1 carbon, then you will be getting this product, second product, right? But if hydrogen is removed along with this Br from carbon 3, this one, then you will get this product. Now among these two, in the first case, 3 alkyl groups are attached to doubly bonded carbon, but in the second case, 2 alkyl groups are attached. So that is why this will be the ZJ product, not this one, and this will be measured 70%, 30%. Fine. Another way also you can explain this if you want to know why the first one is measured. So basically, we know that when alkene CC double bond, it is most substituted. See here 3 substitution present. So most substitution means stability is also high. But the actual reason is here with respect to the CC bond, double bond, these positions are alpha, right? Here with respect to the CC bond, this is alpha position, this is alpha position. Now at alpha position, for the first molecule, 3 alpha position, total number of hydrogen, 9 alpha hydrogen. But in the second case, you have 3 and 2, total 5 alpha hydrogen. So higher is the number of alpha hydrogen in the CC double bond, higher will be the stability. So this is another way you can check that which among these two will be most stable. Fine. So this is ZJ flow. Any doubt? Now when we are talking about elimination reaction, there are 2 mechanisms. Just you have seen in case of substitution there is SN1 and SN2, but now also we will have under elimination 2 different types of mechanisms. So the first mechanism is E1 reaction, that is E1 mechanism. You can find some similarity with SN1 also, because this is also unimolecular. The rate expression, when you will consider, there will be mention of concentration of only the starting material, that is substrate, but not the reagent that you are using. So that is, it is unimolecular, and the term 1 we are using, just you have used the term 1 in case of SN1, and E is for elimination. So this is a unimolecular reaction, and also it is a 2-step reaction, where the rate depends on the concentration of substrate only, but not on the concentration of base that you are using. So right now, as it is elimination reaction, we will use the term base, not nucleophile. You can use the term nucleophile when it is discussion related to substitution, but when it is discussion related to elimination, you have to consider the term base. More stable carbocation is, faster will be the reaction according to the mechanism of E1. So this is also, you can find some similarity with SN1. Rate determining step consists of formation of carbocation intermediate. This is also just like SN1. Order of reactivity, that is also like SN1. And in this case, when you are making alkene, strong base, there is no such requirement. Even if you are using weak base, it is fine. And the reason is same, because in the rate expression, there is concentration of substrate only, not the reagent. So what kind of reagent you are taking, that is not important here. So example is, here we have taken this Me3 CCl, that is, it is tertiary, and tertiary substrate is very good substrate. So this is a slow step, which is first step where carbon chlorine bond is broken, and you are getting positive charge over this carbon. This is 3° carbocation. This is leaving group. Now in the next step, which is first step, the reagent we are using is sodium ethoxide. So basically here the base is ethoxide. It will capture this hydrogen, which is beta hydrogen, because with respect to this carbon, all these positions are beta. Sorry, I mean to say with respect to this chlorine, this is alpha carbon, all these are beta. So any of these beta hydrogen you can consider, which is removed by TO minus. This CH bond will be broken, there will be CC bond, and finally you are getting alkene. So here Cl minus that is removed, now it is attached to the sodium ion, and ETO minus, as is it has taken this beta hydrogen, now it is ethanol. Okay, so these are the side products. So this is E1. What about E2? Now E2, when we are saying 2, that means it is bimolecular and it is single step. So you can find similarity with SN2 also. But it is not that always there will be similarity, whose rate depends on both the concentration of base as well as substrate. See, in case of E1, it is only the concentration of substrate that is significant, but here you have to consider the concentration of both base and substrate. And order of reactivity, as you have seen in case of E1, it is 3°, 2°, 1°, but for E2 reaction there is no such preference. Fine. And here one criteria must be present, and that criteria is the CX bond, that is the carbon halogen bond, and the carbon beta hydrogen bond. So these two bonds that are broken in elimination, right? So these two bonds must be in anti-periplanar orientation. The meaning of the term anti-periplanar, planar means these two bonds must be in the same plane. That is the first thing. And the second point is they must be anti to each other. So when we combine these two terms, it becomes anti-periplanar. Here we have taken 2° substrates, CH3, CHBr. Basically, this is the molecule CH3, CHBr, then CH3, isopropyl bromide. Here it is single step reaction. ETO minus is attacking any of these beta hydrogen because all these are beta hydrogen. CH bond broken, CC double bond form, Br is also there. So in this mechanism, you will not be able to understand the anti-periplanar orientation because here both CBr and CH are drawn in the same. But actually, if you want to see the anti-periplanar orientation, it will be like this. So C, the Br I should write down. Fine. H up. Then left hand side there is CH3. And this hydrogen, if it is the hydrogen which is to be removed, we will write it in this way. So this is basically I will write it as CH2. So now see, this CBr bond and CH bond, these two bonds are to be broken so that you can get this type of propane molecule. So these are same plane and also they are anti to each other. So in this case, as if it is drawn as if they are on the same side, but it should be anti to each other. So this is the meaning of the last line. That is the CX bond which is to be broken and the CH bond that is also to be broken. So these two must be anti to each other. That is the meaning of this line. Okay, CBr and CH. Any doubt about these two types of mechanism? Here we will see this problem which is very simple. The major product A in the following reaction that will be the formed. You have to find what is the structure of A. 4 different options are given. Here we have this 4 carbon chain attached to benzene ring, and this carbon is containing Br. You are using methoxide ion, so this will behave either as nucleophile or as base. Now, if you are thinking why I have written both of them, because see, if you look at option 1, option 3, option 4, all these are basically substitution reaction. There is no CC bond, but only in option 2 there is CC bond formation. That means it is acting now as base, but if it is substitution reaction, it is acting as nucleophile. So that is why I have written nucleophile, or it may behave as base. Now if CH3O minus, it is behaving as nucleophile, then this should be the product, substitution product, not this one, because Br cannot be exchanged by HO. Here the nucleophile is CH2O minus, MEO minus, so which this is not correct. And here see this OMe, it is at para position, but it will not do so, because here this type of H replacement by methoxy, that is not possible. So 1 and 3 not possible at all. But there is two possibility. If it is behaving as base, then this is alpha hydrogen, this is beta hydrogen, alpha carbon, this is beta carbon, so this is beta hydrogen. So this CH bond will be broken, this CBr bond broken, you will be getting CC double bond. So this is elimination product and this is substitution product. But which of these will be actually formed? Because we have we know conditions are almost same, and when conditions are same and there is a chance of both elimination and substitution, then what you can consider? You can consider the stability of final product. So the final product that you are seeing here and the final product that you are seeing here, in case of option 2 product, the CC double bond that is formed, that is adjacent to pH ring, right? There are two more carbon. Now pH ring, this double bond, it can take part in resonance with the double bonds of the benzene. So as a result, there is resonance possible. So that is why this product, as it is resonance stabilized, so we have to give more importance towards elimination reaction, not substitution. So that is why your final product will be this one. So correct option is option 2. That is the elimination product. See, CH bond is broken by the base, and then CBr bond is also broken. Here it is written E2, but we will go to that in detail why it is E2. Remember here, whether it is E1, E2, that is not important, but it is elimination, not substitution, because here the CC double bond, it can take part in resonance with the double bonds of benzene. So final product, as it is resonance stabilized, so that is why option 2 is the correct option, but not substitution. That is not option 4. And option 1 and 3, these two are not possible at all. You can easily cancel it out. But there is a chance that 4 will be formed, and even it may be the minor product, because it is asking the major product. But these two cannot be formed. Okay. So in today's class, is there any doubt regarding any slides? So as there is no doubt, we are ending the session here. Thank you for listening.